Before we get started, I have a quick favor. I've been self-funding the Finding Genius podcast for 5 years now. I've done over 3,000 episodes. And as you can see on YouTube, we're up over 1 million views on the channel, which is fantastic. The next thing I really want to push on is to get up to 10,000 subscribers. Because once we do, we'll be able to put a donate button and we'll be able to solicit donations to help keep the podcast running and to also get the Finding Genius Foundation moving along. We have a big project studying anxiety, depression, and PTSD and working on a product to help people overcome these problems because I've seen them explode recently after the last 2 years of the whole virus situation. So if you would, please subscribe to the podcast. That would help us tremendously. Give us a thumbs up and check in the description for Buy Me a Coffee. It's about $5. If you could buy me a coffee, I'd really appreciate it. It would help keep the channel going, and I love coffee. Thank you.
Forget frequently asked questions.
Common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. My guest is Dr. Heidi Hammel. She's the Vice President for Science at Aura Incorporated, AURA. We're going to talk about the astronomy they do, how it interfaces with the James Webb Space Telescope, maybe some info about the possible origins of life and various planetary systems. So welcome, Heidi. Thanks for coming.
Hey, it's a pleasure to be here. Thank you.
If you would, tell me a bit about your background, and then let's talk about your current work.
Sure. So I was trained as an astronomer. I have a PhD in physics and astronomy. And most of my work in the field of astronomy, when I was an active astronomer, was in the field of planetary science, particularly studying things within our solar system. Because back when I was a young astronomer, we didn't have planets around other stars that were known to us. That's, of course, changed over the course of my career. We now know of thousands of planets around other stars. But I still have a focus on objects within our own solar system. Today, I am Vice President for Science at Aura, which is an organization that runs very large telescopes for the U.S. government. We run ground-based telescopes at Kitt Peak and Cerro Tololo. We have the Gemini Observatory under our management, which is 2 very large 8-meter class telescopes, one in Hawaii and one in Chile. And we're building a new ground-based telescope called Rubin Observatory down in Chile, which will be a completely new type of telescope. And that's all on the ground. We also run big telescopes in space. Most listeners will be familiar with the Hubble Space Telescope. We've been operating that for over 30 years. And now we also are running the Mission Operations Center for the James Webb Space Telescope in Baltimore, Maryland. I had a special interest in that because I have actually been one of the scientists for the James Webb Space Telescope for over 20 years. So it's wonderful to be part of an organization now that is actually running that facility in space.
So, your pick, what's some of the most interesting work you're doing right now? Is it with James Webb? Is it in other areas? And then we can do deep dive on it.
Yeah, so there's the science programs that I'm involved in, and then there's my day job, which is different. In terms of the science programs, as one of the 6 interdisciplinary scientists for JWST over the past 20 years, I had 100 hours of guaranteed time with this brand new telescope. And my program for James Webb was using James Webb Space Telescope to look at objects in our solar system, from near-Earth asteroids all the way out to the edge of our solar system, out there at the Kuiper belt where Pluto resides, and everything in between. So my 100 hours of guaranteed time went to observing Mars, asteroids, comets, Jupiter and some of its major moons, Saturn and its interesting moon Enceladus, Uranus, Neptune, and dozens of Kuiper belt objects. So if you have your favorite, I'm happy to talk about that. To me, they're all marvelous, so it's hard for me to pick what my favorite is. I spent most of my professional astronomy career studying at the ice giants, Uranus and Neptune, so they do hold a little bit of a special place in my heart, and we've gotten some great JWST observations of those planets already. But they're all great. Everything in the solar system's great.
Well, let's start with the stuff that you like. So Uranus and Neptune. What have you observed about them, and what does some of the new imagery show?
Yeah, I think when I saw the first images of Neptune, I started to cry because they were so beautiful. I mean, I knew they were going to be great, but I didn't realize that we'd be able to just image the ring system of Neptune straight out. Like, just you take a picture, there are the rings. And, listeners may be saying, what's the big deal about that? Well, we hadn't seen the rings really since Voyager in 1989. We've tried with the biggest and most powerful telescopes that we have, and we can get little hints of some of the brightest parts of the rings, but the fainter dust sheets, they've just been invisible to us. And the very first JWST image, there they were, rings. And so that was it was really moving. And
you know what it reminds me of? When every once in a while, if I see a movie from the 1980s, I think, how did I even look at the screen? The resolution's so bad. And now it's so much clearer. And James Webb's the same thing. It's like black and white to color, or it's just, crappy resolution to amazing resolution so far. Yeah. Really great imagery.
And it's not even just resolution, it's sensitivity. It's like the ability to see faint things. And of course, JWST was designed to see things. It was designed to see the faintest galaxies in our universe. That was the purpose of JWST, to see the very first galaxies that ever formed, which are incredibly far away and incredibly faint. And so, that was why we built it, to be so powerful. But the good thing for the rest of the universe is that if you can see the most distant galaxies in the universe, you can see everything in between, including faint rings around the planet Neptune. So that's, I think, why the community, the broad astronomical community, is so excited about JWST, because whatever field they're in, whether it's faint galaxies or star formation or studying exoplanets, or like my team studying the solar system, JWST is so powerful. It allows us to make discoveries that we just never even thought we would make. It's so exciting.
Is there any point in getting imagery of close objects, like let's say the moon with JWST, or is it really only meant for, extreme field type observations?
So there's a distinction between close and bright. So we can't look at the moon. We've designed JWST with these big sun shields. If you've seen a picture of JWST, it's got this big tennis court sized shield, and that shield is designed to always be between the telescope and the sun, the earth, and the moon. That's what it was designed to do, because they're just too bright. So we will never look at the moon, unfortunately. But in terms of things that are close by, like asteroids and Jupiter, the people ask me, why are you looking at Jupiter with JWST? Haven't we sent dozens of spacecrafts by it? Don't we have an orbiter there now? And I'm like, yeah, we do. But here's one example. When we looked at Jupiter with JWST, it is so sensitive that on the shadowed edge of Jupiter, it was able to pick up a haze, or haze is the wrong word, a bright layer glowing in the infrared that had never been seen before, because it's so faint compared to the bright Jupiter. But JWST was sensitive enough to pick up this glow. And when we first saw it, we didn't even know what it was. Really, what could be glowing in the atmosphere of Jupiter along the edge there? And after a long time and many debates, we think it is some kind of a high-altitude ionospheric glow from the aurorae that is somehow being distributed around the high altitudes of the Jupiter. But, this is a brand new discovery made by pointing this telescope at Jupiter, even though we have many spacecraft by there and have it orbited there right now. The technology that we're using, the wavelengths we're using, the sensitivity we have is so different that we are able to make new discoveries. And that's why we're using it in our solar system. That's why we used it to look at Mars, for example. But we have rovers on the surface of Mars and helicopters. Yeah, we do. But with JWST, we can measure the infrared emission from the atmosphere and from the surface all over the whole planet all at once, which allows us to make new measurements about the chemistry of the atmosphere that we can't make with those rovers who are going around looking at the rocks. Do you see what I mean?
Well, in terms of capacity and in terms of observation, would it be ideal if we were able to put the appropriate telescope in orbit on all the planets in our solar system? What would, I know it'd be an amazing dream to do something like that, but would it be very useful? What do you think that would do if we're able to do something like that?
So we have this debate in the solar system community all the time. People are like, why don't we build a Hubble or a JWST just for solar system? And I'm like, yeah, you know what? These are very difficult, very expensive, very complex missions. I don't think we're going to build one to just look at Mars or look at Uranus or look at Neptune. I mean, I'd love that, but that's just not realistic. It took us 20 years and 20,000 people working in multiple countries around the Earth to be able to build JWST.
And look at some of the other big projects, the humans have done, sequencing the human genome. Now it's 1 billion times, trillions of times faster and cheaper. Wouldn't you expect that the technology for telescopes would follow the same trajectory if it was invested in?
Before we continue, I've been personally funding the Finding Genius podcast for 4.5 years now, which has led to 2,700 plus interviews of clinicians, researchers, scientists, CEOs, and other amazing people who are working to advance science and improve our lives and our world. Even though this podcast gets 100,000 plus downloads a month, we need your help to reach hundreds of thousands more worldwide. Please visit findinggeniuspodcast.com and click on Support Us. We have 3 levels of membership from $10 to $49 a month, including perks such as the ability to see ahead in our interview calendar and ask questions of upcoming guests, transcripts of podcasts you're interested in, the ability to request specific topics or guests, and more. Visit findinggeniuspodcast.com and click Support Us today. Now back to the show.
Maybe
I do. That's why we have a JWST. That's why we have a JWST. The question is, do you want to spend every single dollar for science on astronomy? I'm not sure. I think that the reason that we do projects like JWST is that they are powerful enough to fundamentally change our understanding of the universe. That's what's happening right now with JWST. And we are already looking to the future right now. I mentioned my day job. My day job working at Aura is I am working with our partners to try to build the next telescope that will come after JWST, the next large one that we think might be able to actually characterize dozens of Earths around sun-like stars and perhaps find evidence for life in the atmospheres of those Earths. That's a telescope called Habitable Worlds Observatory. And we're working right now to lay the groundwork to make that telescope reality. It's not going to be next year. It's not going to be 5 years from now. If we're lucky and work hard, it might be 10 or 12 years from now. It took 20 years to build JWST. So these are not easy.
Yeah, what would this telescope that you're talking about, what wavelengths would it look at, and why would it be able to discover if there's life or not when others can't?
Yeah. So we're designing this one to use the same wavelengths that Hubble is. Hubble goes from the ultraviolet wavelengths of light, that's bluer than our human eyes can see, to what we call near infrared, just a little bit redder than our eyes can see. So it covers all the visible wavelengths. So Hubble is a telescope that is like an extension of our human eyes, but a little bit better. JWST is an infrared optimized telescope. So it starts at the red and goes much further into the infrared. And so it's not what our human eyes can see. So what we're imagining for this next telescope is to go back to the Hubble wavelengths, to the ultraviolet visible wavelengths, and then make it not the size of Hubble, which is a 2.4 meter aperture telescope, but make it much larger, like 6 meters. Or if Heidi Hammel controlled the universe, it would be a 12 meter or a 15 meter telescope. It would be like Hubble on steroids. And the reason you need to do that, to look for life, is that JWST doesn't sense these visible wavelengths. Like, Earth is a pale blue dot. That color blue is a visible color. JWST doesn't have the sensitivity at that wavelength. It just doesn't do it. It was not designed for that because it was designed for a different scientific purpose. So this telescope, Habitable Worlds Observatory, would be designed to work at the blue wavelengths so we could find the pale blue dot around another star and spread the light from that planet, that pale blue dot, into its rainbow of colors and look for the fingerprints of things like oxygen, methane, carbon dioxide, ozone. That's what we need to do to be able to tell if that planet is potentially habitable. Does that make sense?
Yeah, well, that tells me that there really should be twin observations of everything we're observing, right? Both Hubble and James Webb. You'll see different aspects.
You are exactly right. And that's why we're so happy that Hubble and Webb are working together. But Hubble is a 30-year-old telescope. First of all, it's 30 years old. And it's, you imagine your car, 30 years. Things get a little creaky sometimes, and we don't hold out hope that Hubble's going to last forever. It's doing great right now. It has its bad days. The gyroscopes on it sometimes, which we use for pointing, sometimes the gyroscopes get a little get creaky, like your knee gets creaky or your elbow gets creaky, and it doesn't work so well.
Are there plans to upgrade Hubble or just launch something else to replace it and then kill it once it's dead or let it die?
We do have to boost its orbit. Right now it's in a low Earth orbit, and we do have to boost its orbit. We don't want it to crash to Earth. But you know what? Think about this. If you've got a 30-year-old car, right, and it's just poking along, do you want to just keep repairing the 30-year-old car, or do you want to buy a modern car with modern capabilities and everything that goes with that? To answer the question that we laid out, is there life on another world? Hubble's not powerful enough to answer that question. And JWST is not the tool. It wasn't designed to do that. And so if we want to answer this question, are we alone in the universe? We need to build the right tool to answer that question. And that's Habitable Worlds Observatory. And you know what? We could do that in our lifetimes. We could be the generation of humanity that discovers life elsewhere in the universe. That's within our grasp.
What if we only discover what we put out there? Because microbes do take rides on all kinds of vessels and crafts. I mean, Voyager 1 and 2.
That might be true in our solar system, because we do know that rocks are exchanged between the Earth and Mars and the Moon and Earth. So we know in our solar system that material is transported amongst our different worlds here. But that's not going to be possible with planets around another star. The distances are just, dare I say, astronomical. There's no communication of material between another star system and our star system. So we, humanity, could not seed life on planets around other stars. So if we do see evidence on a planet around another star, that is a different emergence of life in the universe than ours in our solar system.
So if you could have your dream, how many telescopes and how would they be tuned to observe a planet in every which way you'd want? What would be the ideal suite of observations that we could make, and with what kind of instrumentation?
We have a dream right now called the new Great Observatories. When Hubble was launched 30 years ago, it wasn't only one telescope by itself. There was Hubble, but there was also the Spitzer Space Telescope, and there was the Compton Gamma Ray Observatory and the Chandra X-ray Observatory. So we had this sort of suite of telescopes back then that covered the full range of all the different kinds of light that comes from the universe. And so our dream for today is that we build a fleet we call the new Great Observatories, of which JWST would be the first of this new generation, but Habitable Worlds would be the second. And we also imagine an X-ray telescope to fill in the X-ray realm. And we also imagine a far infrared telescope beyond JWST. And so if we had those 4 observatories flying all together, we would have this full complement from ultraviolet, X-ray through ultraviolet, visible, near infrared, far infrared, all the way out to, we would have the ability to observe the universe with new tools, better sensitivity. That'd be my dream. So 4 telescopes, that's what I'd argue for. But honestly, I'll take one, which is Habitable Worlds.
Yeah. So now back to some of the features you were talking about. So you mentioned the Kuiper belt. For people that don't know, which is partially, where is it? Is it what function does it appear to serve? From our vantage point on Earth, and again, some details about it.
Sure. When we were exploring the solar system in the 50s, it sort of like ended at Neptune, right? Pluto had been discovered by Clyde Tombaugh all by its lonesome out there beyond Neptune, but the astronomers in the 50s and 60s speculated that the solar system didn't just stop at Neptune. They speculated that there was more material out there, and Pluto was the only one that was found, right? But starting in the 1980s, and then since then, we've actually discovered tens of thousands of objects orbiting the sun out beyond Neptune. Pluto is one of the largest ones, but it may not even be the largest one. There's another one, Eris, an object that's, about the same size as Pluto and possibly even larger. And there are a handful of others that are of comparable size to Pluto. So I call Pluto like the king of the Kuiper belt, but it's out there with 10,000 of its closest friends and relations. And these objects, they're balls of ice and dust all put together in some are balls, some are oval shaped, some are just weird rock shaped depending on their size. And why should we care? Well, the reason we astronomers care about the Kuiper belt is we noticed that they weren't randomly distributed around the sun. Their orbits actually clump in distinctive ways. And those distinctive ways have to do with Neptune and Uranus, and they resonate with their orbits. They kind of dance together with that. Pluto does too. Pluto has a special little dance it does with Neptune. And by looking at that field of stuff there, we actually can read the history of our solar system. We can actually figure out how our solar system formed. And so the Kuiper belt is like the key to solar system formation. It's kind of wild that these little rocks that out there beyond Neptune are telling us the story of how our solar system came to be.
How come the material on the Kuiper belt doesn't accrete and form like a planetoid, or how come it doesn't all smush together at some point, especially if it's crowded into preferential orbits?
Yeah, that's a great question. And I think the answer is that Neptune is actually migrating outwards. Like the orbit that we see Neptune in today, that's not where Neptune formed. Neptune's orbit is getting slightly larger over time. And because of that, it's moving out into that area where those objects are and stirring them up, right? Some of them get captured into preferential orbits that are resonating with Neptune, but others are scattered by Neptune out into weird, strange, large oval shapes. And so Neptune's motion over many, many billions of years is actually stirring that stuff up. It's kind of the same as our asteroid belt in the inner solar system. Between Mars and Jupiter, we have this region that's just filled with all these asteroids, these chunks of rock and a little bit of water and ice. And why didn't they form a planet, right? The answer in that case is Jupiter. Jupiter's moving inward with time, and Jupiter's inward motion is stirring up the asteroid belt, so they can't form the planet there, even if they wanted to. So that's why we don't have those extra planets. It's the big ones are causing trouble. Jupiter's causing trouble for the asteroid belt. Neptune causes trouble for the Kuiper belt.
One thing comes to mind from what you said. I'm thinking about the structure of an atom. So I guess supposedly 99% of the mass in our solar system is contained in the sun, like the nucleus of an atom. And then the preferential orbits reminded me of the energy levels of electrons, around the nucleus of an atom. So I wonder if the solar system, is it all similar to the structure of an atom?
Well, in a very rough sense, yes. The difference being that those energy shells in atomic terms, they don't migrate inward and outward. That's the fundamental basis of quantum physics. What that word quantum means in quantum physics is it refers to these specific shells of electrons, and they come at discrete locations, only those locations, and they don't move. That's the quantum part of it. Whereas in the solar system, the planets are far more flexible, and they can drift inward with time, and they can migrate outward with time as well. So I see what you're saying, but it doesn't quite map. Our planets are not fixed. And I'll share with you that if people don't know that, that's okay. When I was learning planetary science 30 or 40 years ago, we didn't know that. We didn't know that the planets migrated with time. That's something we've learned just, in my career as a planetary scientist. Science progresses and changes with time. That's one of the things that people sometimes misinterpret about science. They think it's about knowing facts and that facts don't change. But in fact, science is a process of asking questions and trying to understand what we observe. And when we observe these different classes of Kuiper belt objects, the only way to explain that is by having Neptune migrate outwards. And so we've changed our understanding of solar systems over just in my lifetime. It's who knows what we'll be learning in the decades to come. It's a very exciting time to be an astronomer.
Well, if you try to go backwards in terms of the age of the solar system, were the planets, you think, that in a different order in terms of their distance from the sun? Like what information does the Kuiper belt formation give you about the early structure of the solar system?
That's a really, really good question. And in fact, when people do really detailed computer models about how our solar system could have evolved to show the Kuiper belt as it is now, there are in fact some models that have Neptune closer in than Uranus. And then at some point, it got into a resonance with Saturn, and Saturn kicked it out further out closer to where the Kuiper belt is now. And so there's a possibility that the order of the planets today, the four giant ones, Jupiter, Saturn, Uranus, Neptune, could have been, when we started, Jupiter, Saturn, Neptune, Uranus.
What about the composition and structure of the planets? Does that show that they preferentially would have started in a different position in relation to the sun?
The trick is that the critical information about that, you have to actually measure in the planet itself. The things that we use as tracers of where things formed are things that don't change over time. So things that like have oxygen and hydrogen and nitrogen, there's a lot of chemistry that can take place and change over time. So you have to look for something that's not going to change over time. That's going to be your tracer. And we call those the noble gases: argon, xenon, neon. The problem with noble gases is that they don't react with things. So the only way to measure them is to send a physical probe into the atmosphere and make the measurements there. We've done that only for Jupiter. The Galileo spacecraft had a probe and it sent it into Jupiter, and we were able to measure these elemental abundances of noble gases. When we dream about the missions that we would like to have to Uranus or Neptune, we absolutely want to put an atmospheric probe on it so it'll go into the atmosphere and measure that so we can answer the question that you just asked. Right now, we just don't have the tools to do that. We need a mission that has an atmospheric sampler.
Okay.
So you're asking all the right questions. You would be a very good planetary astronomer.
Yeah, I appreciate it. What do you think is likely to happen, let's say, in the next 5 years in terms of observations or new material that's being launched? Any new telescopes or instrumentation or patches or upgrades or anything that's going to broaden our view in the next 5 years? Or right now it's just a matter of running James Webb and training it on everything we can to get as much data as we can?
We actually have a couple of things happening that are going to be absolutely great that are coming down the pike. In terms of space telescopes, we have a telescope right now in development called the Roman Space Telescope. It's named after Nancy Grace Roman. She was a chief scientist at NASA many decades ago, and she's the one who kind of made the Hubble program a reality. So we've named this new telescope the Nancy Grace Roman Telescope. And what's special about Roman is that it is a visible wavelength telescope like Hubble. It's in fact the same size as Hubble, but we've designed the optics of it to be a wide field telescope. So instead of a small, tiny postage stamp in the sky like we get with Hubble, we would be able to get a very large picture at the same time. And that will allow us to do a different kind of science much more effectively than we can do with Hubble. Here's an example. Let's say I wanted to look at the Andromeda Galaxy with Hubble. It would take me hundreds of pointings of Hubble to build up a picture of this very large galaxy. But with the Roman Space Telescope, one picture, boom, you've got the Andromeda Galaxy. So that's super powerful. And that is scheduled for, I should have made some notes, so I'm doing this from my memory, so you might need to fact check.
Well, with that, could you...
That's going to launch in a couple of years.
So with that, what if you pointed it at the Andromeda Galaxy and you got a wide depth of field, but similar depth of field, and then you ratcheted it outwards, so you could do like almost like an MRI Andromeda Galaxy. You do a wide field observation at a certain distance, and you go a little bit further, a little bit further, a little bit further. Could you do that and raster your way through it and get like a 3D image of it, wide field?
Yeah, so there's deeper and there's wider. And so to get like a 3D, you have to go deeper, right? See,
That's what I mean. Could you?
yeah,
do like
longer exposure, right?
With
Yeah.
this new telescope, could you do a successive set of images where you go deeper and deeper and deeper with the same width, and then be like,
Absolutely. I mean, yeah, for sure, definitely. That's part of the beauty of it, and you can do it in a reasonable amount of time too. I mean, you don't have to do like 500 pointings and then 500 longer pointings. So that's the power of it. And the other thing about having a wide field telescope is that you capture like more of the sky. So in addition to the Roman Space Telescope, we have that telescope, a telescope called the Rubin Observatory. This is a ground-based telescope that we're building down in Chile, where we have many other telescopes. And it, too, is a wide-field telescope. And it's going to be incredibly powerful. What it can do is image the entire southern sky in 3 days, the whole sky in 3 days. And then it goes back to the beginning and images the whole sky again. And every 3 days it does that, but it does it for 10 years. And so what that allows us is a whole new way of studying the sky, because we're seeing the whole sky changing every 3 days. So if a supernova pops off in a galaxy nearby, we can see it and we have the data, for all. You don't have to be looking at that particular galaxy. It'll just come out of this data set. So using Rubin and Roman together is going to put us in a whole new type of astronomy, which we call time domain, watching things change in the sky over time. It's going to be a brand new way. It's data intensive, of course. There's huge volumes of data. So now people are starting to, or have been exploring machine learning tools to use to delve into these large data sets. That's just going to be fascinating to see what we learn from this new way of studying the sky. It's going to be really amazing.
Well, very good, Heidi. Where can people go to see some of the amazing imagery coming from these telescopes and to keep tabs on your work in particular?
Sure. So for JWST stories, there's a website called webbtelescope.org. The Webb has 2 B's in it, webbtelescope.org. All of our Hubble data is at Hubble Site. That's the name of the website, Hubble Site, SITE.org. If people want to stay on top of all these new facilities that Aura is building, Aura has a website that links to all of our various centers around the world. So there's a lot of different places that people can go, and they can follow JWST, Hubble. They can follow me on the various social media channels. I try to put a lot of stuff out there. So I hope that's some of the resources people can look to. And
Yeah, no, that sounds good.
NASA.gov. NASA.gov always has plenty of good stuff too.
Excellent. Well, Heidi, thank you so much for coming on the podcast. I really appreciate it.
You're very welcome. And thanks for your great questions. Really appreciate it.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.